The diversity and complexity of celestial bodies in the universe are truly astounding. Among them, neutron stars stand out as mysterious treasures of deep space due to their unique and extreme physical properties, attracting the endless curiosity of the scientific community. One particular neutron star, RxG 1856.5, 3754, has captured the special attention of astronomers because of its relatively close proximity to Earth. However, despite being closer than many others, it is still approximately 400 light-years away, a distance that is insurmountable given current human technological capabilities. At present, we lack the means for direct contact and exploration across such vast interstellar spaces, not to mention conducting complex and hazardous excavation activities on a celestial body as extreme as a neutron star. Although reality presents numerous seemingly insurmountable barriers, the vast realm of science allows imagination and theoretical predictions to open windows to the unknown. Let us imagine a scenario filled with science fiction yet provoking deep thought. If we were able to extract a spoonful of material from this distant neutron star and bring it to Earth, what complex chain reactions and unimaginable consequences might ensue? To thoroughly and systematically analyse this hypothetical situation, we first need to determine the exact mass of this mysterious spoonful of neutron star material. Neutron stars are some of the densest objects in the universe, second only to black holes. Their density is 13 grams and 2 x 1015 grams per cubic centimetre. For the sake of more complex calculations and in-depth analysis, we can make a series of reasonable and representative assumptions. Suppose we set the density of the neutron star material at 1014 grams per cubic centimetre, and the volume of this spoonful of material is 10 cubic centimetres. Using basic physics formulas and simple mathematics, will these mysterious substances from the neutron star under Earth's gravitational pull plummet straight to the Earth's core like a meteor? However, a thorough scientific analysis and rigorous theoretical deduction provide a negative answer. The key factor that allows neutron star material to maintain its astonishingly high density state is the extremely strong and nearly ubiquitous gravitational environment of the neutron star. The gravitational force on the surface of a neutron star reaches unimaginable extremes, strong enough to crush and warp atomic structures to expand rapidly. The enormous energy released during this expansion would cause a significant and destructive explosion on Earth's surface. However, it is crucial to emphasize that this is only the initial manifestation of a series of severe consequences, merely the prelude to a potentially catastrophic event. As the rapid expansion continues, the tightly bound neutron star material transforms into a large number of free neutrons. These free neutrons are inherently unstable and will inevitably undergo a decay process. The half-life of free neutrons is relatively short, approximately 611 seconds. This means that every 611 seconds, half of the existing free neutrons will decay. This process continues until the decay nears completion and reaches a relatively stable state. Neutron decay is a specific form of beta decay where the neutron transforms into a proton, releasing an electron and an antineutrino. Through meticulous study in the field of particle physics and precise measurements, we know that a neutron's mass is about 1.6745 x 1027 kilograms. A proton's mass is about 1.6726 x 1027 kilograms, and an electron's mass is a mere 9.00956 x 1031 kilograms. The mass of the antineutrino is negligible in most calculations. With these precise scientific data, we can conclude that during neutron decay, there is a notable, though not minor, mass loss of approximately 0.15% of the initial mass. If all 10 trillion kilograms of neutrons were to undergo decay, the mass loss would be around 1.5 billion kilograms. However, in reality, not all neutrons will fully decay. During the decay process, free neutrons will interact and combine with protons and electrons in the surrounding environment, forming large quantities of stable atoms like hydrogen and helium. To facilitate further calculations and analyses, we can adopt a conservative yet meaningful approach by halving the estimated mass loss to about 750 million kilograms. The crucial question then arises: where does the mass lost during decay go? Albert Einstein's famous equation provides a clear and insightful answer. The seemingly vanished mass is released as a form of highly potent energy. By strictly following Einstein's principles and methods, we can determine that the energy corresponding to the 750 million kilograms of mass loss is approximately 6.75 x 10 to 25 joules. To better understand the immense scale and potential impact of this energy, we can compare it to significant historical events on Earth. Approximately 66 million years ago, a massive and powerful asteroid struck Earth, triggering the Cretaceous Paleogene extinction event. This catastrophic event led to the extinction of dinosaurs and many other species. Based on comprehensive and rigorous estimates and analyses from geological evidence and mathematical models, the energy released during the asteroid impact and subsequent chain reactions was tremendous. The energy released is approximately 3.4 x 1023 joules. Through simple and direct comparison and calculation, it becomes apparent that the energy released during the decay of a spoonful of neutron star material is roughly equivalent to the total energy from 200 massive and incredibly powerful asteroid impacts on Earth. Such a release of energy would have a series of catastrophic and almost irreversible consequences for our planet. First, let's delve deeply into the implications for Earth's ecosystems. This massive energy explosion would cause irreparable damage to the rich and diverse biological systems on Earth. The planet's ecosystems consist of a complex, intricate, and fragile web of interdependent relationships between countless species. This energy impact would be akin to an unstoppable super tsunami, instantly devastating vast ecological areas, leading to the loss of habitats and the collapse of ecological networks. The forest ecosystems, as one of the Earth's key ecological pillars, would be the first to suffer. The powerful and irresistible energy explosion would ignite vast areas of forest, causing trees to be mercilessly destroyed, burned, and toppled. Many species that rely on forest ecosystems would suddenly lose their homes and food sources. This disaster would not only directly cause the immediate death of countless plants and animals, but also trigger unpredictable and uncontrollable chain reactions, profoundly affecting and destabilizing the entire forest ecosystem. Similarly, marine ecosystems would not be spared from this disaster. The instant release of energy could trigger enormous tsunamis and abrupt changes in ocean temperatures, causing catastrophic impacts on marine life. Plankton, fish, shellfish, and other marine organisms would face large-scale death and extinction. The collapse of the oceanic food chain, a key mechanism for maintaining marine ecosystem stability, would have impacts far beyond the ocean itself. Since the ocean plays a crucial role in global climate regulation and ecological balance, its destruction would have profound and potentially irreversible impacts on the climate and ecological stability of the entire planet. For land and freshwater ecosystems, the situation is equally dire and bleak. Rivers, lakes, wetlands, and other freshwater systems would suffer severe pollution and destruction, with many freshwater species facing extinction. The high temperatures and radiation from the energy explosion could rapidly deteriorate soil quality, severely affecting plant growth and agricultural production, directly threatening human food supply and survival. From a geological and geophysical perspective, the immense energy release would trigger unprecedented earthquakes and volcanic activity. The Earth's internal structure and plate movements, previously in a relatively stable and balanced state, would be disrupted like a massive earthquake, causing intense crustal movements and deformations. Intense earthquakes would occur globally, with magnitudes and destructive power far exceeding any recorded in human history. Buildings would collapse instantly, infrastructure would be completely destroyed, and countless lives would be lost amidst the tremors. Additionally, earthquakes could trigger landslides, mudslides, and other secondary disasters, further worsening the destruction of the Earth's surface and endangering lives. Volcanic activity would also be highly stimulated by this large-scale, high-intensity energy release. The magma within the Earth would, under the impact of this tremendous energy, break through the crust with even greater ferocity and form unprecedented volcanic eruptions. Volcanic ash and scorching lava would spread over large areas, causing direct and lethal harm to surrounding environments and organisms. The vast quantities of gases and fine particles released by volcanic eruptions would enter the atmosphere, having profound impacts on global climate and atmospheric circulation, further exacerbating environmental degradation and uncertainty. Furthermore, this energy explosion would have significant and far-reaching impacts on the Earth's atmosphere. The massive energy input could cause the atmosphere's temperature to rise sharply in a short period, altering its composition and circulation patterns. This would lead to a series of extreme weather events, such as unprecedented superstorms, devastating floods, and prolonged droughts, causing long-term instability in the global climate. The ozone layer, a critical shield protecting Earth from harmful ultraviolet radiation, could be severely damaged by this energy impact, exposing the Earth's surface to increased ultraviolet radiation, posing additional threats and harm to biological survival and reproduction. The structure and stability of the atmosphere could also be severely affected, potentially leading to the stripping and loss of parts of the atmosphere, further altering Earth's environmental conditions and living space, plunging the planet into an unprecedented crisis and challenge. From a microscopic physics perspective, a deeper and more detailed analysis of the decay and energy release process of neutron star material involves some of the most profound, subtle, and fundamental principles and mechanisms in atomic physics and quantum mechanics. During the decay process of neutrons, weak interactions play a crucial and indispensable role. Although relativities and the uncertainty principle, the specific details and paths of decay exhibit a certain degree of randomness and unpredictability. From the perspective of the internal structure and interactions within atomic nuclei, the mutual conversion between neutrons and protons involves strong interactions within the nucleus. Strong interactions, with their powerful forces, tightly bind nucleons together, forming a relatively stable atomic nucleus structure. However, under specific extreme conditions, such as during the decay process of neutron star material, this originally stable equilibrium is disrupted, leading to neutron-to-proton conversion and energy release. These intricate microscopic physical processes at the macroscopic level manifest as large-scale significant energy explosions and material transformations, further highlighting the close and complex intrinsic connections and interactions between the microscopic and macroscopic worlds. Through in-depth, it is important to emphasize that such an extreme situation is almost impossible to occur in the real world. Currently, human technological levels and capabilities are far from achieving close proximity and material extraction from neutron stars. Moreover, even in the distant future, when technology has achieved unprecedented progress and breakthroughs, we must evaluate and consider the potential risks and unpredictable consequences of such a venture with extreme caution, responsibility, and scientific rigor, as well as its profound impact on the Earth and human living environment. In humanity's long journey of exploring the universe, we must always adhere to scientific principles, methods, and ethical boundaries, advancing our exploration and understanding of the unknown world responsibly, sustainably, and with respect for natural laws. Our goal should be to continually enhance our profound understanding and knowledge of the universe through scientific research, rather than blindly pursuing risky and short-sighted actions that could lead to destructive consequences. At the same time, This hypothetical scenario and theoretical exploration provide us with a valuable opportunity and perspective, allowing us to gain a deeper and more comprehensive understanding of Earth's fragility, the complexity of ecosystems, and the infinite mysteries and unknowns of the universe. It ignites our curiosity and desire to explore the unknown, driving continuous innovation and progress in science and technology. In future scientific research and exploration, the intersection and collaborative innovation of astrophysics, particle physics, earth sciences, and other related fields will become an inevitable trend and direction. Through interdisciplinary research and comprehensive analysis, we hope to gain a more comprehensive, in-depth, and accurate understanding and knowledge, continually exploring, innovating, and breaking through to reveal more unknown mysteries about the universe and Earth, providing a more solid and reliable scientific foundation and guarantee for humanity's future development and survival. Therefore, while the idea of placing a spoonful of neutron star material on Earth is practically a fantasy, by deeply discussing and analysing this scenario, we can significantly expand the boundaries of scientific thought and deepen our understanding and comprehension of the universe and Earth. This not only aids us in persistently advancing on the path of scientific research and courageously climbing new heights, but also constantly reminds us to cherish our unique and precious home planet, Earth, with a cautious, respectful, and reverent attitude toward the universe's unknowns and challenges.